Okay, so a couple of announcements for you. I mentioned that this first unit goes, just so you are aware, our first test, our first exam will be 2 weeks from today. I believe that's February 2nd. So that comes up rather quickly, just so you're ready for it. But it is these basic topics. And today we are going to continue with some of the basic topics just because there are some of those background concepts, like we talked about the count and the name on Monday. There are some background concepts like that involved in these basic operations that help us when we get into some of the more complex math, some of the algebra. So the concept we're going to look at today that ties that count and name into the bigger picture of math a little bit is the concept of place value. I know you've all seen place values before and you know what they all are, so we'll make the review portion of this really quick. I'm looking at the number starting at the decimal point, working my way backwards. Of course, we know that first place value is the ones, tens, and then hundreds. Those are actually the only three place values we have. They get repeated over and over again. Ones, tens, hundreds. And again, ones, tens, hundreds. And they get repeated as many times as we need to repeat them in our place values. So these groups of three place values, this first group is just our base group. Then, of course, we have the thousands group, billions group, billions group, and trillions group, and all the way up the line. Most of us will probably never encounter anything above the millions. Really, you have to almost get into national budgets before you get above the millions group. I'm not going to insult you by going through how to name each place value, but it is important that, for several reasons, that we know what those place values are and that we can identify digits in those place values. One of the reasons it's important is I might ask you to do something like this. Round 3,784 the nearest 100. Of course, we all know how to round, but let's look at what this really means. Technical definition of rounding, when we're asked to round to the nearest 100, that's the key word here. What it's implying is that we have a number line that is only numbered in hundreds. So like 3,600, 700, 800, 900, and so on. So when we look at our number that we're rounding, round to the nearest 100, we find the digit in the hundreds place. Of course, that's the 7. That is telling us that the number is between 3,700 and 3,800. Now we take that number, 3,784, we put it on our number line, and we can see that physically it is nearest or closest to the 3,800. Well, 3,784 rounded to the nearest 100 is 3,800. Because again, on the number line, physically, that's the 100 that it's closest to. Now, we don't want to draw out number lines every time we draw numbers, so we've learned shortcuts. And, well, we should. The shortcut that most of us were taught was to identify that hundreds place. Again, that was the 7. But then to tell whether it's closest to the 3,700 or if it's closer to the next one up, the 3,800, we look at that next digit. If that next digit was a 1, 2, 3, or 4, we knew it was closer to the smaller one, the 3,700. If it was a 6, 7, 8, or 9, it's closer to the bigger one, the 3,800. Of course, the question always comes in, and that's why I left it off for now. What if that next digit is a 5? What if this were something like 3,752? Find our hundreds digit is 7, and that next digit's a 5. Well, we've been taught that you're going to round up if that next digit is a 5. Still rounds up to 3,800. In grade school, when we were learning rounding, if you had asked why to do that, you might have been told, well, we just accept that we do, or it's a convention that we've come up with. But there's a little bit more to it than that. If we place this on the number line, it's 3,752. It actually is slightly closer to the higher number. So when that next digit is a 5, the reason we always round up is because generally it is closer to that next number. The only time it would be perfectly in the middle, if it were 3,750 exactly. For the purposes of this class, and in most cases, that next digit's a 5, you're still going to round up to 3,800. The only exception to that is when you get into mechanical engineering, mechanical design, machining. There are some exceptions there where when that next digit's a 5, you might round it down. We're not going to go through those examples here because I don't want to confuse you. For this course, if that next digit's a 5, we always round up. Another big reason why those place values are important is for explaining why we do our process of our basic operations the way we do. Let's look at a number like 473. We're used to looking at that and seeing that as being the full number, but it's not. That's actually an abbreviation. The full number there is really 4 hundreds, 7 tens, and 3 ones. That is the full form of that number. We see it written that way. We can see now that this is not just a 7, it's a 7. Every digit of that number is a count and a name. So if we go to add them, let's say we're going to add it to 200 and again, we'll write that out. That's really 200s, tens, and 4 ones. Remember, we said on Monday that when we add and subtract, we can only combine things that have the same name. That comes right down to the place value. These tens can only combine with other tens, and the hundreds with other hundreds, and the ones with other ones. That's why it has been stressed to us through the years. When you add and subtract, you have to line up those columns. Once they're lined up, we can go ahead and add. 400s and 200s make 600. 10. And 4 ones make 7 ones. That's 697. Now, you may have noticed, if you watched closely, that I did something a little strange there. I started on the left, and I worked my way to the right as I added. Typically, we go the other direction. We start at the end of the number, and we work our way back.
Got to see in there.
We're part of that in case we have to here. We have something like 279, 300, we start on the right and work backwards because we'll have 9 plus 8 is 17. Two digits in the same place, so 7. Carry the 1. 9 plus 7 is 8, plus 4 is 12. Again, 2, carry the 1. 1, 2, and 3 make 6. Believe it or not, though, I mean, we've been taught that that's the only way to add numbers. It's not. There are several other processes to add numbers. One of them looks like this. Plus 3 is 5. Plus 7, so 1, drop the 1. 9 plus 8 is 17, so 7, drop the 1. 5 plus 1 is 6. 1 and 1 is 2. 7. Notice we get the same answer, just a little bit more space taken up, maybe a little bit more work. Now, I'm not trying to change the way you add numbers. The point I'm trying to make is, In math, we've been told that there's only one right way to do things. That's not true. There's only one correct answer, but there's often several methods you can use to get to that answer. I can show you a couple other ways to add numbers that'll work out every time. I'm not going to do it because I don't want to confuse you, but the point is that just because you don't do things exactly the same way I do does not mean you're doing anything wrong. If you have a different way of doing things and you're not sure if it works all the time, let me know and I'd be happy to look at it, go through it with you. I'm also a realist. I understand you have calculators and the calculators will be used. But before you use the calculators, at the very least, I would hope you would look at this and say, that's about 300. That's also close to 300. Combine 3 plus 3 is 6, and keep the name of hundreds. I'm expecting an answer close to 300, to 600. The reason I say you should do that is because on a calculator, it is really easy, and it happens to me a lot, to do something like this, 279 plus 348. 8 didn't register when I typed it in. 317, if I'm not paying attention, I'm going to write that down and assume it's correct because the calculator is always right, and move on. Or something like 279 plus 348. 3,000, again, if I did this estimate, I know that's not correct. But I accidentally hit an extra key with my sausage-like fingers. And I got an extra number in there. Again, this estimate isn't going to catch every mistake, but it catches these really bad ones like this. Of course, subtraction happens the same way. We use the place values have to be lined up because we can only combine things with the same name. I'm not going to write them out in long form because I think you guys get the picture. But I will go ahead and do an example. 748 minus 235. Once we have them lined up, those columns lined up, hundreds and tens and ones, we can just go ahead and subtract the columns. 7 minus 2 is 5 hundreds. 4 tens minus 3 tens is 110. 8 ones minus 5 ones is 3 ones, giving us 500. Now you might have noticed again that I went backwards. I started at the left and I went to the right. That's the opposite of what we've been taught. To start at the end of the number and work backwards. For subtraction, it's in case we have to borrow. So we might have 926 minus 387. We have been taught to start at the end of the number here. 6 minus 7 can't be done, so I'll borrow from the 2. 1. This is now 16. 16 minus 7 is 9. 8 can't be done, so I borrow from the 9. That's an 8. This is now 11. Minus 3 is 5. Again, that's not the only way to subtract. You could very well do this. 9 minus 3 is 6. 2 minus 8 can't be done, so I take from the 6. That's a 5. This is a 12. 12 minus 8 is 4. 6 minus 7 can't be done. I take from the 4. That's a 3. This is 9. Again, not trying to change the way you subtract, just making that point that there are several different methods, algorithms for subtraction that would still work. Multiplication. 32 times 21. This one I will write out in its full form. 32 is 3 tens. 21 is 2 tens. And 1 1. If you recall from Monday, we talked about when we multiply and divide, we do not need the same name. Which means these 3 tens not only can be combined with the 2 tens, but combined with the 1 1. In fact, every digit in one number can be combined with every digit in the other number. And that's all that long multiplication is an organized method to make sure that every digit in one number gets combined with every digit in the other number. So here, let's take Now, the thing that varies really from one process to another is usually where we start. We've typically been taught to start the bottom number and that last digit, so the 1 in this case. Then we start combining it with the top number with its last digit. So 1, 1 times 2 ones. Now we do have to remember to deal with the count and the name. For the count here, 1 times 2 is just 2. For the name, 1 times 1, well, anything times 1 is itself. It's just 1. Then we move over to the next digit of the top number. 1, 1 times 3 tens. Well, again, we combine counts. 1 times 3 is 3. Then we combine names. 1s times 10s is 10s. Again, anything times 1 is itself. Now we've used every digit in the top number, so on bottom, we move over to the next digit. And we've been taught that when we do that, down here, we either have to put in a 0 or leave a space. Well, the reason for that will be apparent here in this next step. Now we have the 2 tens times the 2 ones. Again, we combine counts. 2 times 2 is 4. But we also combine the names. 10s times 1s is 10s. Leaving that 0 here was just a way of making sure we keep our place values lined up. 10s with the 10s. Now we move over again. 2 tens times 3 tens. Times 3 is 6. 10s times 10s is hundreds. And now we can combine, like place values, 2 is only 2 ones, 3 tens and 4 tens make 7 tens into 600, 672. Again, I'm a realist. I realize long multiplication is not something that most people are going to do by hand. A lot of times I'm going to throw it in the calculator myself. But understanding the process and the reason for it, if you do have to do it, might help you remember the process. Something we haven't talked much about is combining the counts. We just kind of assumed that you knew how to combine the counts. And I'm going to continue to do that, but let's just briefly mention a multiplication, 5 times 3. If you think back to first grade, before you memorized your multiplication tables and before you just knew 5 times 3 was 15, how did we figure that out? We were taught to just do 5 plus 5 plus 5. 3 5s added together. Multiplication is defined to be repeated addition. Well, we said that division follows many of the same rules as multiplication. So if I look at 24 divided by 8, can I do 24 minus 8? 16 minus 8, that would be 8. 8 minus 8 is 0. Because I subtracted 8 1, 2, 3 times. And yes, 24 divided by 8 is 3. Division can be thought of as repeated subtraction. This is where our remainders come from. I have 27 divided by 6. Start out with 27. Minus 6 is 1, 21. Minus 6 again is 15. Minus another 6 is 9. And minus another 6 is 3. I can't take 6 away from that anymore without going below 0. I subtracted 1, 2, 3, 4 sixes. So 27 divided by 6 is 4 because I can subtract it 4 times, with a remainder of 3 because there was 3 left over. When we get to larger numbers, let's say we have 84 divided by 2. I'm not about to start subtracting 2 from 84. We don't have that kind of free time. But what we can do is we can subtract large bundles of 2. This is the tens digit, so let's look at 10 times 2, 20. If I subtract 20, what I have really done is I've subtracted 2 10 times. I subtract 20, I'm at 64. Another 20, I'm at 44. Another 20, I'm at 24. And one more 20 puts me at 4. I have subtracted the 2, 10, 20, 30, 40 times. By subtracting in big bundles, I was able to subtract it rather quickly, subtract the 2 40 times. Now I still have the 4 left over. I'll subtract the 2 and another 2 to get to 0. That's 41, 42 times. 84 divided by 2 is 42, because I can subtract the 2 42 times. Now what I just did here, subtracting 2 in big bundles, in this case subtracting the 20, so I can subtract it 10 times a shot, that is what long division is based off of. What I'm about to show you is where the process of long division that you were taught came from. It's not going to look much like what you were taught, but it is. So if I have, I'm just going to make up a number here, 79,243 divided by 21. How do I know how big? I'm definitely not going to start subtracting 21 from 79,000. How do I know how big of a bundle to start subtracting? Well, I look at the number I'm dividing, and I look at the place value of that first digit. That 7 is in the 10,000s place. We'll start with that. 10,000 times 21 is 210,000. Can I subtract that from what's there? No, that's too big. So I go to the next place value. 1,000 times 21, 21,000. That I can subtract. In fact, I can subtract it more than once. 21 could be 60,000. Now, I could have subtracted 21,000 over and over again, but by multiplying it by 3, it allowed me to subtract it 3 times all at once. So I subtract, I got 16,243. Well, what I really did here was I subtracted 1,000 to 21s. Each 21,000 was 1,000 to 21s, and I did that 3 times. 1,000 times 3 is 3,000. When I subtracted the 63,000, what I was subtracting was 3,000 to 21s. Then I moved to my next place value. So my next place value is 100. 100 times 21 is 2,100. I can subtract that from what's left. Looks like 7 times. 2,100 times 7 is 14,100. Subtract that, 3, 4, 1,543 is what's left. Now again, what I did there, I subtracted a bundle of 121s. The 2,100 was 121s, and I did it 7 times. 100 times 700. That 14,700 was another 721s. My next place value would be 10s. 10 times 21 is 210. I can subtract that from what's left. Oh, let's try 7 times. 7 times 210 is 1,407. Subtracting, that gives me 373. So again, that's a bundle of 10 21s. The 210 was 10 21s times 7. 7 times. Times 7. That was subtracting another 70 21s. And finally, we're down to just the ones. Of course, 1 times 21 is just 21. We can subtract that here times. 21 times 3 is 63. There's 10 left over. So we just subtracted it 3 more times. 3,773 with the remainder 10. So when we divide 79,243 by 21, we get 3,773, remainder of 10. Now, as I told you, you might be looking at that thinking, that looks nothing like what we've been taught. But as I mentioned, it's exactly what you were taught. It's what we were taught is a severe shortcut. What we were taught to do was look at this and say, this 21 go into 7. Well, no, it doesn't. So leave it blank here. That's what we did over here. That was too large, so we went to the next place value. Over here, we go to the next place. Is 21 going to 79? Yeah, it goes in there 3 times. 3 times 21 is 63. We subtract to get 16. That's exactly what we did over here. We just left out all the zeros. So we go ahead and bring down, now depending on what method you were taught, either just bring down the next digit or you bring down the rest of the number. It doesn't matter which. 21 goes into that 706 or 162 7 times. 7 times 21 is 147. There's 15 left over. Again, that's exactly what we did over here. We just left out zeros. So this process that we were taught for long division comes from this process of just doing repeated subtraction, subtracting out large bundles, basically, of that divisor at a time. That's all long division is. Now again, I don't do long division by hand. I use the calculator if at all possible. So I admit that that's most likely what you're going to do. But at the very least, look at this and say, okay, this is about 80,000. This is about 20. 80,000 divided by 20. 8 divided by 2 is 4. 10,000 divided by 10 is 4,000. I'm expecting an answer close to 4,000. Have that estimate in your head before you divide, so you know if your calculator really something up. So we have talked a lot about combining counts, but we haven't done much of it, where it comes from. We just assumed you know how to do it. We did the 5 times 3 and turned it into repeated addition. But let's take a look at addition, subtraction, and how we combine those counts as well. To do that, we need to look at how do we represent a count. In other words, a count. And when we come to calculating, the best way to do it is something called a vector. Vector is a very fancy term for a very simple concept. Let's say I want to find the vector for 4. Vector for 4 is simply an arrow that starts at 0 and goes to 4. That's its vector. Very useful representing the numbers because now when I add, addition is just defined as combining vectors. What do I mean by that? Well, let's do 4 plus 7. I have the vector for 4 there. The vector for 7 would look like this. If I am adding those numbers, what I would do is I would take this vector for 7 and I would put it on the end of the vector to 4 and combine them into one long vector. We see now that this combined vector is 11 units long. 4 plus 7 is 11. Now, we didn't need to do the vectors for 4 plus 7 because we all know how to add 4 plus 7. But we're not always going to be working with positive numbers. I have something like 8 plus a negative 3. Vectors help us to represent that. I have my vector for my 8, just like this. My vector for negative 3, like this. And if I move that vector for negative 3 over to the end of my 8, it actually works against it. It comes here back to 5. 8 plus negative 3 is 5. The vector picture allows us to combine those negatives with our positives without having to think about it really too much. Now, I don't expect we're going to draw vectors to scale every time we add with our integers, with our negative numbers. But I do keep that picture in my mind when I am working with integers. If I have something like 47 plus negative 62, what I am thinking is this. Here's 0. 47 goes the positive direction. It's like that. Negative 62 goes the opposite direction. And now these vectors have two qualities. They have a direction, which is the positive or negative, but they also have a magnitude, their length. 62 is a bigger magnitude than 47, so it's going to go past 0 into the negative side. So this vector diagram, even though it's not to scale, tells me two things. One is my answer is negative because I end up on the negative side of 0. 2, since the vectors go in opposite directions, the length of my result is the difference in their magnitudes. The technical name for their magnitudes is called absolute value. It's simply the length of the vector. So here, the absolute value for the negative 62 is just 60. The absolute value for the 47 is 47. The difference there is 15 units. So the result here is 15 units, negative 15, because the vector diagram shows we end up on the negative side. We might have negative 23 plus a negative 38. Now again, here's what I'm picturing. Start at 0. Negative 23 goes this way. Negative 38 goes the same direction. That tells me that I definitely end up on the negative side. And because the vectors go in the same direction, the magnitude of my answer is found by adding the magnitudes. I have 23, and that adds to make 61. So this is a negative 1. Like I said, I don't expect you to draw out the vectors every time you deal with negative numbers, but keeping that picture in the back of your mind helps you to understand what you have to do to combine them. Subtraction can be a little trickier. If I do 8 minus 3, if I asked you to draw a vector diagram, most people would come up with the same diagram. It would look like this. 8 at 3, we end up at 5. We all know that 8 minus 3 is 5. We've done enough subtraction that we can come up with that answer. But if we look at this picture over here, that picture looks an awful lot like 8 plus a negative 3. Because it is. We had mentioned that subtraction is part of addition. The technical definition of subtraction, that symbol there, means add the opposite. The opposite of what? Well, the operation operates on the number that comes after it. So in this case, it would be the 3. 8 minus 3 is 8 plus the opposite of 3, which would be a negative 3. Now again, 8 and 3 were both positive. We know how to subtract those, so I wouldn't bother changing that. If I have something like 48 minus 16, I'm just going to do 48 minus 16 is 32. I'm not going to turn that into adding the opposite. But if I have a negative 27 minus 34, that's a little more confusing because I'm starting with a negative number. But if I change this, the first number doesn't change, the negative 27 does. Remember, the subtraction operates on the number coming after it. So instead of subtracting 34, we're going to add the opposite of 34 is a negative 34. Now from 0, we have negative 27. 34, this is going to be a negative 1. One that people kind of get stumped on is this one. We might have 38 minus a negative 19. Again, the 38 doesn't change. The subtraction operates on what comes up after it. Subtracting a negative 19 is adding the opposite of negative 19, which is a positive 19. 38 minus a negative 19 is the same as 38 plus 19. So, now that we looked at multiplication as repeated addition, multiplying something like negative 5 times 3 isn't a problem. We add 3 negative 5s together to get negative 15. In fact, most of you are probably taught negative times a positive is a negative. Where we run into some difficulties is when we have 5 times negative 3. Now, most of you are probably still taught, well, positive times a negative is a negative. It's just negative 15. And that is the correct answer. But the reason why is this. We had mentioned on Monday that when we add or multiply, if we run into issues, sometimes we try to just switch the numbers. And that's what we can do here. Turn that to negative 3 times 5. Now it's just saying take 5 negative 3s and add them together. Is a negative 15. That makes sense. The one that does not make sense, red, this one. Negative 5 times negative 3. Now, most of you have been taught a negative times a negative is a positive, so you know this answer is going to be positive 15. The question is why? According to our definition of multiplication, this is telling us to take negative 5 and add it together negative 3 times. Well, I can't do something a negative number of times. If I switch the order, I make that negative 3 times negative 5, that's still saying take negative 3 and add together negative 5 times. I can't ask me to do something a negative number of times. The way we get around it, this actually happens quite a bit in math where the basic definition breaks down and doesn't work, for an example. But what we do is we establish a pattern. We look at the problem that we can use the basic definition. And we change one thing. In this case, I'll do a negative 5 times 2, be a negative 2. And we observe if a pattern is created. Let's continue doing what we did. We changed this by 1 from 3 down to 2. Let's take it from 2 down to 1. Negative 5 times 1 is a negative 5. And what we get here is a pattern. When we reduce this by 1, this number gets larger by 5. From 2 to 1, that's reducing it by 1. From negative 10 to negative 5 is going up by 5. And this pattern continues. Negative 5 times 0, I reduced that by 1 again, is 0. That went up by 5 again. If I keep going, negative 5 times negative 1, well, this went down by 1. This has to go up by 5. 5. Negative 5 times negative 2, again, it has to go up by 5 to 10. Positive 10. Negative 5 times negative 3, again, it increases by 5. The only reason that a positive times a negative times a negative gives us a positive is because it completes the pattern. Otherwise, according to the definition of math, it doesn't. You guys obviously know the rules. Negative times a positive is a negative. Positive times a negative is a negative. If both are negative, a negative times a negative is a positive. That applies for multiplication, and it also applies for division. But again, only because of the definition of a division. If I look at 15 divided by 3, of course we know that equals 5. But it's actually defined through something called a related multiplication problem. The related multiplication for this is basically working backwards, starting with the 5 times 3 equals 15. That is the related multiplication problem for that division. So when we're looking at solving a division problem, what we're doing is filling in a blank in that related multiplication problem. So if I have negative 28 divided by 4 equals blank, the related multiplication problem is blank times 4 equals negative 28. Well, we know that for this to be negative, we have to multiply one positive and one negative. Since this is positive, this number has to be negative. That's a negative 7 times 4. It's negative 28. Therefore, negative 28 divided by 4 is negative 7. Negative divided by positive is negative. If I have 36 divided by negative 9, that's asking what number times negative 9 equals 36. For this result to be positive, we know we either have to have two positive numbers multiplied or two negative. If that's negative, we know this one is also negative. Or positive divided by a negative is a negative. Or we might have negative 40 divided by 10. That's asking what number times negative 10 is negative 40. Again, for this to be negative, we need one positive and one negative. That's negative. This one has to be positive 4. Negative divided by a negative is a positive. Again, I realize this is all review of stuff you guys have seen at least a couple of times. But hopefully seeing some of the background information helps. We're about 2.5 minutes early, but I'm going to go ahead and give you your homework. In your book, it is page 7 and 8, problems 1 through 59, the odds. Now, as I mentioned, most of you have seen this stuff before. As you're doing the homework, the first couple of problems might seem easy. If that's the case, please feel free to skip ahead to the more difficult problems. Make sure if there are word problems, make sure you do the word problems at least, because that's what people tend to struggle with. I don't want you to sit at home doing busy work on stuff you already know how to do. That's one of the reasons I don't collect the homework in this class. I'm not telling you not to do the homework. Do enough of it so that you are relatively sure that when we get to the test next week, you know how to do it. Now, one of the reasons I quit a couple minutes early here, I had mentioned test 1 is coming up next week, 2 weeks from today. That's February 2nd. And on test 1, there is a section where you must show your work. And what I mean by that is you must show 428 plus 356. You must show 8 plus 6, that's 4, carry the 1. You must show those steps so that I see that you can do that by hand. And we will do that. We will be done with whole numbers, fractions, and decimals. It'll be about 14 or 15 problems. I'm not saying you can't use your calculator. Please feel free to use your calculator to double check your answers. But also make sure you show those steps so that you know that you can do them. The reason I do that, I know it's a little old-fashioned, but I was a structural engineer, a construction engineer before I came into education. It was not uncommon for me to get to a job site and have my calculator got dropped in the sand, and there are buttons that are not working anymore. I use the calculator. Or my calculator got tossed in the windshield and the sun warped and it doesn't work. I know now you have calculators on your cell phones. Dating myself a little bit, I didn't have cell phones back then. But having some basic calculated math skills is pretty useful. Well, like I said, practice what you need to up there. Make sure you do any word problems. With that, you guys go. We'll see you on. Oh, by the way, scheduling. I have the schedule almost made out. What I have done is looking at the scheduling. Any days that there's 2 or more schools that are out of session, we'll be canceling class. So unfortunately, that leaves a number of days where one school is out. I know Clear Lake, you guys are gone this Friday for an in-service. Unfortunately, we'll be having class. So if you want to, if you need me to send that link for Blue Jeans, it's in Blackboard. If you want to look it up there, you can log in home. Otherwise, I will be posting the recording from class within about 10 or 15 minutes after the end of class on Friday. So you can look at that recording. I'll have the homework is also posted. There's a recording from last spring. Or if you want to just go ahead and get the stuff done for Friday ahead of time if you would like. The homework is posted for Friday and Blackboard. Have a great day, and we'll see you on Friday. Thanks.